It's May 12th. Rapidly approaching the end of the quarter. So let's see, more double integrals. So let's actually do that double integral that we started with last class that we kind of got diverged from, which was the following. It was the integral from 0 to 9 of the integral from the square root of y to 3 of 1 over the square root of x cubed plus 9. And so now that I've written this, you all should be able to know if it's supposed to be dy dx or dx dy. Specifically, it is going to be, drumroll please, dx first, dy second. And the dx comes first because the inner integral, that is an x equals the square root of y, and that is an x equals 3. So the x here has to match up with the x there. And then this is a y equals out here, and the y equals out here. But we absolutely know that it has to be an x equals here because you couldn't have y equal to the square root of y. That wouldn't make any sense. Great. Normally they're just going to give it to you the right way anyway, but it's good to know what to expect. Okay, so now the problem with this integral is you cannot find an antiderivative of 1 over the square root of x cubed plus 9. Doesn't exist. There is no function whose derivative is equal to that. So when you see something that looks like it might be impossible or just really, really hard, the usual go-to thing to do is to reverse the order of integration, which we practiced last time. So we're going to rewrite this. Actually, we're going to draw the region first. I'm going to draw the region here. So I've got x equal to the square root of y. And x equal to the square root of y. It looks very much like y equal to x squared, except x has to be positive. So it's only the right-hand side of that parabola. There's x equal to the square root of y. And over here, here's x equal to 3. And then the y values. So my horizontal strip, because that's what this is representative of, if my inner thing is x equals, I'm going as far left as x equals square root y, as far right as x equals 3. And then those strips are going as high as 9, as low as 0. Although I would usually probably say it the opposite way. That point there is definitely the point 3, 9. So I want to reimagine this region using vertical strips. So using vertical strips, my lower bound of my vertical strip is y equals 0. And my upper bound of my vertical strip is still x equals square root of y, but I have to solve for y. So y equals x squared. And then we can rewrite this, and then we're going to go as far left as 0, as far right as 3. So we're going to rewrite this as double integral. My inner limits of integration are going to be y equals 0 to y equals x squared. Still the same integrand. The integrand doesn't change. But now at the dy first instead of the dx first. And my outer limits of integration are going to be x equals 0 to x equals 3. Cool. So we've appropriately interchanged the order of integration, and now we can definitely anti-differentiate this thing with respect to y. If there aren't any y's there. If there aren't any y's there, we're just pretending this is one big constant. And the antiderivative of one big constant is that one big constant times y. What we're going to get here is the integral from x equals 0 to x equals 3. And then let's use some parentheses here. The antiderivative of 1 over the square root of x cubed plus 9 with respect to y is going to be 1 over the square root of x cubed plus 9 times y. From y equals 0 to y equals x squared. Still with a dx. So all I did was anti-differentiate that, which was super straightforward because it was just a constant. And now look what happens. When we plug in x squared for y, we're going to get the integral from x equals 0 to x equals 3. And I'm going to get 1 over the square root of x cubed plus 9 times x squared minus 1 over the square root of x cubed plus 9 times 0. I'm not going to write that part because it's kind of annoying, So what I'm gonna have here is just x squared over the square root of x cubed plus 9. Want to make sure everyone's seeing that, right? I've got 1 over that times x squared minus 1 over that times 0, which just ends up being x squared. That. And now the good news is this is going to be really easy to do a u substitution for. We can let u equal x cubed plus 9, and then my du is going to be 3x squared dx. So 1/3 du is going to equal x squared dx. And since we're doing a definite integral, I might actually just change the limits of integration as well and do this all in terms of u. I will point out in the notes, I did do this problem as well, even though we didn't do it in class. And I did it kind of a different way I'm about to do it, where I did the integration and then plugged back in what x was. I'm going to do it a different way here just to show it a different way. So if we do it this way, we're going to be getting, so x squared dx, that's going to become my 1/3 du. I have 1/3 du. And my square root of x cubed plus 9 is going to be just the square root of u. And if x equals 0, well, if x equals 0, then u is going to be 0 plus 9. So x equals 0, u equals 0 cubed plus 9, which is 9. And if x equals 3, u equals 3 cubed plus 9, which is 27 plus 9, which is 36. Let's simplify this just a little bit before we finish it. This is going to equal 1/3 times the integral from 9 to 36. 1 over the square root of u is u to the minus 1/2. And now we're going to anti-differentiate. We're going to get 1/3 times, let's see, the antiderivative of u to the minus 1/2 is u to the positive 1/2 divided by 1/2, or multiplied by 2, from 9 to 36. We don't have to change back to x's because these are u values. So we're just going to plug in and we're going to get 2/3 times 36 to the 1/2 minus 9 to the 1/2. 36 to the 1/2 is just the square root of 36. This is really 2/3 times 6 minus the square root of 9 is 3. And 2/3 times 3 is just 2. All that work for 2. Kind of cool. It's nice when it comes out nice. Questions about any of what we did here? Sure. Yeah. So, okay. I'm going to set up the next example. Josh will be back soon. It's kind of weird talking to an empty room, but I can do it. Let's do, let's do one more. Let's look at this next one. Yeah, let's do a dy dx. So let's say we have, call that problem 1. Label things here. And after that, I think we'll talk about sequences because that's where we're going for the rest of the quarter pretty much. So number 2. We're pretty good here. I think we're already doing that much. So number 2, let's do the integral from 0 to 3 of the integral from e to the x to e to the 3. So just based on what I've written here, no matter what the integrand is, I know it's going to have to be a dy dx. Because my inner limit of integration is y equal to e to the x and y equal to e cubed. So y equals, it has to be a dy first. And then my actual function of integrating is y minus 1 divided by the natural log of y. And once again, I have absolutely no clue how to integrate this. It's probably impossible. It might not be impossible. It's probably impossible. So usually if it looks hard, we should change. So let's see. So let's graph our region. I do really, unfortunately, think you kind of always, I really feel like you need to graph the region like every time. It's just, if you're trying to interchange them, there's no other way around it. Fortunately, we know what y equals e to the x looks like. Here's y equals e to the x. And y equals e cubed, don't get fooled. Y equals e cubed is just a horizontal line. E cubed is a constant. It's like 20 something. So here's y equal to e cubed. And then x is going from x equals 0. So there's x equals 0. And it's a pretty good bet that right there is where x is equal to 3. And of course, that's where x is equal to 3, because if x is 3, y is going to be e to the third, and y is going to be e to the third. That's why they're matching up. So yeah, that x is going to be 3, and the y coordinate is going to be e to the third. So we are looking at this region. And currently, it's being expressed using vertical strips, because we're going from y equals something to y equals something. So that's how things have started off. It is vertical, and we want to reimagine it as being horizontal. The horizontal, we're going from x equals 0 on the left, and this here, this y equals e to the x, is going to change into the natural log of y equal to x, right? Taking the natural log of both sides.
So when we do like vertical and horizontal, we start horizontal because it starts with like y is equal to.
So what I'm thinking of is, I know this is vertical. The current setup was using vertical strips because my inner integral had y equals something to y equals something.
Okay.
Y equals e to the x was the lower boundary, y equals e cubed was the upper boundary. And now when I switch it, I have to go left to right. So I'm going from a left boundary of x equals 0 to a right boundary that is the same function as y equals e to the x, but I have to express it as x as a function of y. Welcome, Hanson. So I got x equal to the natural log of y. So now we're going to rewrite this as a double integral where x is going from x equals 0 to x equals natural log of y. And then my strips, instead of going from left to right, like so before they went from as far left as 0, as far right as 3, now they're going as far down as, what is that y value there? What's my lowest y value in this region?
1.
Yeah, right, because that's where we plug in 0 for e to the 0 and you get y equals 1. And up as high as y equal to e cubed. That is just the top value. And then everything inside here still stays the same. Y minus 1 over natural log of y, but now it's dx dy instead of dy dx. And now we can certainly at least accomplish the first step of integration, right? Because as far as we're concerned, everything inside this integrand is a function of y. And if we're integrating with respect to x, all of this is getting viewed as a constant. That often happens when you've got this kind of problem. Is the inner function is some terrible function of the other variable, so you switch to integrate the other variable first. So doing this, we still get y equals 1 to y equals e cubed. And then our inner integral we're actually going to do, you're going to get y minus 1 over the natural log of y, that's your constant, times x. And x is going to go from x equals 0 to x equals natural log of y, which looks like it's going to work out pretty well. I'm using the parentheses in red here to indicate the stuff that's still the same thing that's in the parentheses there. Now, when we plug this out, I'll actually write it out this time, even though I don't really want to. I've got y equals 1 to y equals e cubed, and the insides are going to be y minus 1 over the natural log of y times the natural log of y minus y minus 1 over the natural log of y times 0 dy. Well, anything times 0 is just 0. I should be more explicit. Well, no, I don't know. And then y minus 1 over natural log of y times natural log of y. Natural log of y is cancel. You're just getting the integral from y equals 1 to y equals e cubed of y minus 1 dy. And that's a pretty straight shot, right? The antiderivative of y is y squared over 2. The antiderivative of 1 is y. You're going from 1 to e cubed, so you're going to get e cubed squared over 2 minus e cubed minus 1/2 minus 1. And I guess we could simplify it a tiny bit if we really have to. That's e to the 6th over 2 minus e cubed, and 1/2 minus 1 is negative 1/2, so minus minus is plus 1/2. I would probably choose to leave it like that. I guess if you really wanted a common denominator, you could write it as e to the 6th minus 2e cubed plus 1 all over 2. I find that not necessary, but it's totally fine.
James,
Yes.
how did you get the lower bound y equals 1?
Sure. So good call. So I wasn't super explicit about it, but that point there, that point is the lower part of the boundary. And so I will say this is where x equals 0, and it's where the e to the x graph crosses the y-axis. So that point there is, well, if x is 0, e to the 0 is 1.
Oh, so like ln 1 equals 0 then, right?
Right.
Okay, thank you.
Cool. Okay. So we'll talk about sequences. Sequences. When I think about sequences, I kind of think about a couple of different things. The things we usually talk about when we talk about sequences are, one, kind of what's the pattern or the formula for the sequence, and two, does the sequence converge to a specific number or diverge and not get close to one specific number? So let's look at some examples. Let's say our sequence an is given by the formula 6n plus 1 over 2n plus 5. And let's write out the first 4 terms. Usually, unless someone has said something otherwise, we typically start at n equal to 1. So a sub 1 would be 6 times 1 plus 1 over 2 times 1 plus 5, which is 7 over 7. I don't really want to simplify it. A2 would be 6 times 2 plus 1 over 2 times 2 plus 5, which is going to be 13 over 9. A3 is going to be 6 times 3 plus 1, 2 times 3 plus 5, which is going to be 19 over 11. And at this point, you might start to see, I mean, we obviously have the formula for the pattern, but what's happening is every time I increase n by 1, the numerator is increasing by 6, because I'm literally multiplying n by 6. So 7, 13, 19, the next one's going to be 19 plus 6, which is 25. And the denominator is increasing by 2. 7, 9, 11, 13. And you can keep finding more and more values, right? A5 would be 31 over 15. And A6 would be 37 over 17. And so on and so on and so on. The other question that we typically ask, other than if you're given the formula, sometimes they want you to find the first 4 terms because it's moderately interesting. But really what we're interested in here is, does this sequence converge or diverge? So a sequence is said to converge if the limit as n goes to infinity of that sequence exists. So an converges if the limit as n goes to infinity of a sub n exists and is equal to a real number, where L is a real number. And here it's totally going to exist, right? If you take the limit as n goes to infinity of 6n plus 1 for 2n plus 5, you can either jump straight to the answer. I guess you do we words. Did we learn L'Hopital's rule at some point in 16A or 16B? I don't actually know. I think the answer is maybe. Like you might have learned it, you might not have learned it, depending on who your professor was. We don't need it here, but you could use it if you wanted to. But I would just divide everything by n. So the limit as n goes to infinity of 6n divided by n plus 1 divided by n, 2n divided by n, plus 5 divided by n. Well, 1 over n, as n gets very, very large, gets very, very small. 5 over n does the same thing. So when you plug this in, you get 6 over 2, which is 3. So this sequence converges to 3. it is getting closer and closer and closer to 3 as n gets larger and larger and larger. Just for example, if n equals 1,000, a sub 1,000 is equal to 6,000 plus 1 over 2,000 plus 5. And if I check my calculator real quick here, 6,001 divided by 2,005 is 2.993, approximately. Pretty close to 3. So it's just like how limits work, right? If a limit exists, then we say that the sequence converges. The limit doesn't exist, we say the sequence diverges. And there's a few different ways sequences can diverge. Let's talk about a couple of examples here. Let's look at this next one. Let's say a sub n is equal to 6n squared plus 1, 2n plus 5. And I guess I could label this one number 3. Label that next one number 4. To me, the writing the terms part gets to be a little bit tedious, but it's good practice. So we can say, okay, a sub 1 is 6 times 1 squared plus 1 over 2 times 1 plus 5, which is still 7 over 7. A sub 2 is going to be 6 times 2 squared plus 1, 2 times 2 plus 5, which is 25 over 9. I would say the real point of writing out these terms is later on when we start trying to go the other direction, when they give us some terms, we're going to try and find the formula. That's kind of why we're talking about this. A sub 3 is going to be 6 times 3 squared plus 1 over 2 times 3 plus 5, which is 55 over 11, which is 5. And then one more, a sub 4 is going to be 6 times 4 squared plus 1 over 2 times 4 plus 5. 6 times 16 is 96, plus 1 is 97, over 8 plus 15 is 13. Interesting. So, great, there's the first 4 terms. Is that particularly helpful? I don't think so. More important question, does the sequence converge or diverge? I will say, usually the language of these questions is, does the sequence converge or diverge? And if it converges, what does it converge to? So in the last question, the sequence converged and it converged to 3. So I should go back and write that down. So in this case, I will point out a sub n equal to 6n plus 1 over 2n plus 5 converges, and it converges to 3. Just to be explicit about what we're saying there. So same idea here. We're going to take the limit as n goes to infinity of 6n squared plus 1 over 2n plus 5. Now for this limit and for the previous limit, we could use our knowledge of rational functions and say, well, I see something here where the degree on top and the degree on the bottom is the same. So the limit's going to be the quotient of the leading coefficients, which is 6 over 2, which is 3. In this next one, though, the numerator is raised to a higher power than the denominator, where the degree on top is larger than the degree on the bottom. What that means for us is that this fraction is getting larger and larger and larger. The top is growing faster than the bottom. You can just say that and say the limit's going to be infinity, or you can do a little bit of work. You can do the same kind of thing we did before and divide everything by n to the highest power that's in the denominator. If I divide everything by n, 6n squared over n, 1 over n, 2n over n, plus 5 over n, we get the limit as n goes to infinity of 6n plus 1 over n over 2 plus 5 over n. The things divided by n still get smaller and smaller because n is getting larger and larger. So 1 over n gets infinitesimally small as n gets large. And so there's 5 over n. Those go to 0. But 6 times n, well, n is getting really, really large. And 6 times a really large number is a really large number. So that's going to be infinity plus 0 divided by 2 plus 0. And infinity divided by 2 is still infinity. So be careful here. The sequence does not converge to infinity. You cannot have something getting closer and closer and closer to infinity. It's not a real number. So when your limit's infinity, the sequence does diverge because the sequence isn't getting close to a specific number. So this sequence, a sub n equal to 6n squared plus 1 over 2n plus 5 diverges. And sometimes, you guys are doing web work, so it doesn't really matter. But sometimes on web work specifically, they'll ask you, in what way does your sequence diverge? Does it diverge to infinity or to negative infinity? Or does it do some sort of thing where the limit just doesn't exist because it's like bouncing back and forth between positive and negative numbers? So here you could say, if you were asked, this sequence diverges to infinity, but you probably won't be asked to do that. Yeah, Josh.
Is that dividing by n process, like L hospital rule?
No, it's definitely not L'Hopital's rule. In fact, so L'Hopital's rule is a totally different thing. L'Hopital's rule can be applied in one of two situations. You either have a limit that's an infinity over infinity type, like this one, right? So in fact, let's go back here. If I have this limit as n goes to infinity of 6n squared plus 1 or 2n plus 5, if I actually plugged in infinity, which is not really allowed, but we're going to do it anyway, you're going to get 6 times infinity squared plus 1, infinity, over 2 times infinity plus 5, which is also infinity. And when you have an infinity over infinity form, it's an indeterminate form, and it's one of the forms where you're allowed to use L'Hopital's rule. So we can use L'Hopital's rule. The other situation where you're allowed to use L'Hopital's rule is if you have a 0 over 0 type of limit, which we probably don't encounter very much. That's not true. You can encounter that type of limit here. So yeah. So for example, or not for example, to kind of see this limit, if you take the limit as n goes to infinity of 6n squared plus 1 over 2n plus 5, the way we apply L'Hopital's rule, if you have an infinity of infinity or a 0 over 0, is you still take the limit as n goes to infinity, but you take the derivative of the numerator and the derivative of the denominator. So limit as n goes to infinity, the derivative of 6n squared plus 1 is 12n. The derivative of 2n plus 5 is 2. And now you've got the limit as n goes to infinity of 12n over 2, or you might even rewrite it as the limit as n goes to infinity of 6n. But as n goes to infinity, 6 times n also goes to infinity. So this still shows the same result. The limit is infinity. Just like in the previous example, we could have used L'Hopital's rule and said the limit as n goes to infinity of 6n plus 1 over 2n plus 5 still is an infinity over infinity type. And if we take the derivative of the top and the derivative of the bottom, be careful, we're not using the quotient rule at all. We're just saying treat the top and the bottom totally separately, take the derivative of each one. Derivative of 6n is 6. Derivative of 2n, or sorry, 6n plus 1 is 6. Derivative of 2n plus 5 is 2. And the limit of a constant is just the constant. So we do get the same result.
So I was a bit confused on how do we know when we use L'Hopital's?
So you can only use L'Hopital's rule if you have a limit where if you actually plugged in when m was approaching or x was approaching, you would get infinity over infinity or 0 over 0. Any other situation, we cannot use L'Hopital's rule. This is specifically and explicitly for those two types of limits.
So that's not 0 over 0.
It's not, it's infinity over infinity. Notably, I will also point out, in this example, after I used L'Hopital's rule once, I couldn't use it again because it's no longer an infinity over infinity type. So usually, if you're using L'Hopital's rule, the idea is every time after you use it, you should try to then evaluate your limits and see, oh, can I plug infinity down and get an answer that is sensible? Or not? Do I get something indeterminate still? So L'Hopital's rule is nice and all. It's somewhat applicable for these examples. Has your teacher for 16C talked about it at all? Talked about its use in these examples? It's fine if he hasn't. I'm just curious.
I think we may have mentioned it, but I'm not.
Okay.
I haven't gotten to this.
Sure. Let's look at an example where it's actually super useful. So let's say we have the following sequence. Let's say we have, it's number 5. Sequence a sub n is going to equal, let's make it not too terrible, James. Let's say it's going to be e to the n over n cubed. They're like, yeah, sure, we'll do E to the n over n cubed, why not? We'll do another one like this too, just to kind of drive home the point. So writing out some terms, A1 is going to be E over 1. A2 is going to be E squared over 2 cubed, which is 8. A3 is going to be E cubed over 3 cubed, which is 27. A4, right? There's no simplifying this, right? E cubed is just E cubed. I'm not like trying to get a decimal approximation here. It's going to be E to the 4th over 4 cubed, 64, and so on. Okay, so what is going on here? Well, if I try to take the limit when I'm asking about converging or diverging, the limit as n goes to infinity of e to the n over n to the third. Well, e to the n gets infinitely large, and n cubed also gets infinitely large. Often in this kind of situation, you're either going to get 0 or infinity. Sometimes it works out to be like a real not zero number. A lot of times it's going to be 0 or infinity. So I'm going to start using L'Hopital's rule. So limit as n goes to infinity of e to the n over n cubed. Word of advice, if you're using L'Hopital's rule, I do recommend writing an L apostrophe H above your equal sign so that the person reading your work knows that you're using L'Hopital's rule. It's not always super obvious if you've done it. That's why I like to write that. Okay, so using L'Hopital's rule, I'm going to take the derivative of the top. What's the derivative of e to the n? E to the n. What's the 3n of n cubed? Oh, what's the derivative? Yeah, 3n squared. Okay. And I'll point out this is still an infinity over infinity type of limit. If you plug in n going to infinity, you get 3 e to the infinity, which is infinity over 3 times infinity squared. And when you do that, you're going to do L'Hopital's rule again. So let's do it again. The limit as n goes to infinity of the derivative of e to the n is still e to the n. The derivative of 3n squared is 6n. Still infinity over infinity, right? E to the infinity still goes to infinity. 6 infinity still goes to infinity. So we do it again.
We keep on doing it until we don't get infinity over.
Right. You can, although you don't have to necessarily, because there's some examples where it's not great, but you always can keep doing L'Hopital's rule as long as you still have an infinity over infinity or 0 over 0. But once you don't, that's why you want to check every time after you've done it, right? Like you do L'Hopital's rule and then you check, okay, do I get a thing or not? And if you don't, if you get still infinity, then you do it again. So now using L'Hopital's rule, I have the limit as n goes to infinity of the derivative of e to the n is e to the n. The derivative of 6n is 6. And now I don't have an infinity over infinity. If I plug in infinity, I get infinity divided by 6. And infinity divided by 6 is still infinity. When do we use this rule? When do we use this rule? Just when it's, no, we can also use this rule when it's 0 over 0. It's less likely to come up in this section because most sequences we look at are probably going to be some sort of infinity over infinity, but you could have one that's 0 over 0. I'll try to throw an example at you in a minute here.
Infinity over infinity is not the same as infinity.
Correct. Infinity over infinity could end up being 0, could end up being 1, could end up being 5, could end up being 3, like our first example. So when I say infinity over infinity, what I really hear in my head is it's an indeterminate form. And the word indeterminate really just means it is not determined. It can literally be any value from negative infinity to infinity and anywhere in between. In this case, it happens to be that this is infinity. So what does this mean to us? It really means that e to the n is always going to outpace or outgrow or grow faster than n cubed. Now, let me ask you all a question that we're not going to do, but we can kind of think about the answer to. What if I asked you about the limit as n goes to infinity of e to the n over n to the 100th power? What do you think that limit is going to be?
Infinity.
It's going to be infinity still. And the reason why is because every time you apply L'Hopital's rule, right, I should point out first and foremost, it is an infinity over infinity form. And so if I apply L'Hopital's rule, the numerator is never going to change, right? The derivative of e to the n is always e to the n. Whereas every time you take the derivative of the bottom, the power is going to become one less. So in the first step, you're going to get 100 times n to the 99th power. And then when you do it again, you're going to get the limit as n goes to infinity of e to the n over 100 times 99 times n to the 98th power. And so if you do this 100 times, right, because eventually you'll do it enough times that the bottom will be a not variable, it'll be a constant. So if you do this enough times, you're going to place like, so here's our second to last step here. You need the limit as n goes to infinity of the derivative e to the n again is e to the n, and you have like 100 times 99 times all the way down to, let's say, 2. And then you've got n to the first. And then the last step will be to take the derivative one more time. You get the limit as n goes to infinity of e to the n over 100 times 99 times all the way down to 2 times 1. And even though that number on the bottom is big, it's not infinity. That's a finite big number. The numerator is getting infinitely large. So this is equal to infinity divided by, anyone know a better way of writing 100 times 99 times 98 all the way down to 3 times 2 times 1? Right. It's 100 factorial. That is just notation that's convenient. So when you see a number with an exclamation point after it, it literally means that number multiplied by every number smaller than it all the way down to 1. It's only good for integers though, or positive integers. We can't do it for like, you can't say like 3.2 factorial. That doesn't have any meaning to us. You can say 3 factorial or 7 factorial, but not negative numbers factorial, not fractions, not other weird things. But infinity divided by a constant is still infinitely large. So what this means to me and means to you really is that exponential functions, then like f of x equal to e to the x, is always going to outgrow or outpace polynomial functions like x to a power. No matter how big the power is, eventually with enough derivatives, the derivative of this will be a constant and the derivative of this will not be a constant. Kind of cool.
So do we, I know we got on like the but we can use it on every single.
No, definitely not. L'Hopital's rule is usually not very widely applicable. I will also point out, you cannot use it if your sequence has a factorial in it to start, because there's no good way, at least for us, of taking the derivative of x factorial or n factorial.
So is that what we just use like what you started with?
Right. We use other ways of kind of elaborating through. Let me show you a couple more examples. Let's say let's go to the flip side. What if our sequence was a sub n equal to say, sorry, I had an example here. Yeah, let's say it's n cubed over 2 to the n. Oops, sorry, I can't see that. Before we do anything, what do we, let's write some terms out. A1 is 1 over 2, A2 is 8 over 4, A3 is 27 over 8, A4 is 64 over 16, A5 is, I don't know, something, 125 over 32, and so on. What do we expect to happen here? Well, which part of this sequence is getting larger faster? The numerator, n cubed, or the denominator, 2 to the n power? Eventually, which part's getting bigger faster? Right, 2 to the n, the thing that's exponential. So we expect, since the denominator is growing more quickly, the fraction to eventually get smaller and smaller and smaller. So we are expecting the limit as n goes to infinity of a sub n to equal 0. That is what I think is going to happen. We're still going to show it, but that's what we think. Now, I will say some professors who are like, well, we didn't cover L'Hopital's rule. You can just kind of say the exponential thing is always going to outpace a polynomial thing, and you're just kind of allowed to say this on 0 without showing the work. I don't know how Lee feels about that. I would still show the work. So I'm gonna find the limit as n goes to infinity of n cubed over 2 to the n. That's gonna be using the L'Hopital's rule. The limit as n goes to infinity of 3n squared over, oh, what's the derivative of 2 to the n? I know the derivative of e to the n is e to the n, but when your base is different than e, there's a little bit extra. The derivative of 2 to the n is 2 to the n times the natural log of 2. Just like, although we never say it, I will just point out that the derivative of e to the n is actually e to the n times the natural log of e. We just don't write the natural log of e because the natural log of e is 1. Still infinity over infinity, so we do it again. Derivative of 3n squared is 6n. The derivative of 2 to the n times natural log of 2. Well, the derivative natural log of 2 is just a constant. The derivative of 2 to the n is 2 to the n times natural log of 2, and then there's another natural log of 2 down there. Okay, it's still infinity over infinity, so we got to do it one more time. So we're going to do the limit as n goes to infinity. Derivative of the top is 6. Derivative of the bottom is 2 to the n times another natural log of 2 times natural log of 2 times natural log of 2. And now you've got a constant over something that's getting infinitely large. And 6 divided by infinity is 0. So this sequence, a sub n equal to n cubed over 2 to the n, converges, and it converges to 0. And I should have pointed out in the previous examples that those sequences diverged. Right? If the limit is infinity, the sequence diverges. Okay, let's go back here for a second. Sorry. So this, right? So I'll just point out here that a n equal to e to the n over n cubed diverges.
James.
Yes.
So I'm kind of confused on like the problem that you just did. I understand that it's 0, but when you did like the A1, A2 thing, where you like did like you plugged it in, didn't
Yeah.
the numerator get larger or no?
It did. What an excellent observation. So the problem here is that if you only look at the first few terms, you might get kind of the wrong idea about what the sequence is doing. So you kind of have to go out a little bit further to see what's really happening. So I'll just point out here that a sub 6 is 6 cubed over 2 to the 6th, which is going to be 6 cubed is 216. 2 to the 6th is 64. 125 over 32, that's close to 4. 216 over 64 is actually a little bit less than 4. And then if we go again, A7 is going to be 7 cubed over 2 to the 7th. 7 cubed is 343. 2 to the 7th is 128. That number is less than 3. So it looks like we've started getting smaller. And if we do a couple more, A8 is 8 cubed over 2 to the 8th. 8 cubed is 512. 2 to the 8th is 256. This is actually exactly equal to 2. And we're getting smaller. A9 is 9 cubed over 2 to the 9th. 729 over 512, which is less than 2. And finally, one more term. A10 is 10 cubed over 2 to the 10th. 10 cubed is 1,000. 2 to the 10th is 1,024. That's less than 1. So if you go far enough, the sequence starts to do what the actual behavior is. But if you only look at the first couple terms, you might be misled by what the sequence is actually doing. Yeah, really
And also,
good question there. An excellent question.
Also, if like the limit is infinity, does that mean it does not exist?
Correct.
Like, okay, so you could
Right.
like say does not exist or infinity.
Right. So yes. So I would say, so in the language of sequences, I would say the sequence diverges, which is equivalent to the limit of the sequence not existing as n goes to.
Okay.
Now, when I say the limit is infinity, I am in those words saying a lot of things. I'm saying, yes, I know the limit doesn't exist. And also, I'm telling you a little bit more about the way in which it does not exist. But you're totally right. When the limit is infinity, that means the limit does not exist. For the limit to exist, it has to be a real finite number. Infinity is not. Okay, we got a couple minutes left. Yeah, let's do one more. Let's look at an example that's going to be part of your, part of our world from now on. So let's say an is n plus 2 factorial over 3n squared times n factorial. It's going to be super extra clear. You cannot just cancel factorials. N plus 2 factorial over n factorial is not the same as n plus 2 over n. They don't just go away. There is some work we can do to make things cancel out, but there's a little more work than just canceling out. Let's write a few terms. A1 is going to be 3 factorial over 3 times 1 factorial. 1 factorial is just 1. 3 factorial is just 6. I'm simplifying here just to kind of show things. So I get 6 over 3, which is 2. A2 is going to be 4 factorial over 3 times 2 squared times 2 factorial. 4 factorial is 4 times 3 times 2 times 1. And the bottom I have 3 times 4 times 2 factorial is 2 times 1. Those actually happen to be the same. So that's 1. 4 times 3 times 2 times 1 is the same as 3 times 4 times 2 times 1. Yeah, okay. Let's look at A3. A3 is going to be 5 factorial over 3 times 3 squared times 3 factorial, which is 5 times 4 times 3 times 2 times 1 over 3 times 3 times 3 times 3 times 2 times 1. Cancel a few things, and you get 20 over 27. So from our very few terms we've looked at so far, I know the other 3, my guess would be things are getting smaller. Now, how small? Maybe going towards 0, but maybe just going towards a small fraction. And maybe we're getting closer and closer to 1/3. I think 1/3 might be the answer. I'm not 100% sure. So here's the process for actually finding this. So if I want to find the limit as n goes to infinity of an, the limit as n goes to infinity of n plus 2 factorial over 3 times n squared and n factorial. Bummer of some news here. Cannot use L'Hopital's rule. There are factorials involved. We have to do something else. So I'm going to simplify some stuff. So here's what you should think about. N plus 2 factorial just means n plus 2 multiplied by every lesser integer. So that's really going to be n plus 2 times n plus 1 times n minus 1, all the way down to 3 times 2 times 1. The bottom, we have 3 times n squared times n factorial is the same sort of deal. It's going to be n times n minus 1, all the way down to 3 times 2 times 1. And I will point out that this part right here, n factorial, and this part right here, which is also n factorial, those definitely do cancel out. Another way of saying this, I'll point out that n plus 2 factorial is equal to n plus 2 times n plus 1 times the rest of the terms, which is n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. But the rest of the terms is just n factorial. You can kind of break off the first couple terms until you're left with the thing that you want to cancel. And this n factorial definitely does cancel with this n factorial. Right? All those terms, n over n, n minus 1 over n minus 1, and so on and so on and so on, definitely do cancel out. So we're left with the limit as n goes to infinity, n plus 2 times n plus 1 over 3 times n squared. And I guess you could use L'Hopital's rule here if you really wanted to, but at this point, you don't need to. I would say you're trying to kill an ant with an atomic weapon. That's a saying people used to say, kind of, maybe, where basically you're using too big of a tool for the thing you need to do, right? Here we can just say, if I multiply off the top, I've got n squared plus 3n plus 2 over 3n squared. The degree on top and the degree on the bottom are the same. So the limit is going to be the quotient of those leading coefficients, which is 1/3. Or if you prefer, you can divide everything by n squared.